This video is for Chapter 7, Section 5. It's all about using similar triangles. We've been studying similar triangles for a couple sections now. At this point, we're just going to use the proportions created by these similar triangles. This video is basically to show examples of how we use similar triangles and the proportions they create. The first one we're going to look at is how we can use shadows. In this first drawing here, the sun is coming down and hitting a flagpole, and it's hitting a person. What's going to happen is the person has aligned themselves so that their shadow ends at the same spot that the flagpole's shadow ends. Because the sun is up at the sky causing the angle with the shadows, this angle is congruent to itself. The other measurement that we're going to look at is the height of the pole and the height of the person. Since the person is standing straight up and the flagpole is straight up, we have a right angle. Here we have angle-angle similarity. And with the two triangles being congruent or similar, we can use proportions created by the shadows and the height in order to figure out x. How tall is the flagpole? This is called an indirect measurement. So we're going to take 5, the length of the person's shadow, and compare it to the length of the flagpole shadow. Be careful, the length of the flagpole shadow is not 10, it's 15. And we're going to set that equal to the height of the person and compare that to the height of the flagpole. These are the corresponding parts. We cross multiply and end up with 5x equals 90. We divide by 5 and we get x equals 18. And this is one way that a person can figure out how tall an object is just by measuring the lengths of their shadow and the shadow created by the object. Okay, so that's one example of similar triangles. The next example we're going to take a look at involves something called the side-splitter theorem. In this triangle here, we have a triangle, large one, being cut by a parallel line with the third side of the triangle. The side-splitter theorem says if a line is parallel to one side of a triangle, then it splits the other side into proportional parts. Well, first we know the corresponding angles are congruent and they share the vertex angle. So the triangles are similar by angle-angle similarity. Now, we can set this up as a proportion. We can compare it the way we would normally compare it, like we did in the previous problem. C, the left side, compares to C plus D. The same way that A compares to A plus B. Now this part's going to get a little bit tricky, but this is why we do this on the video so that we get to see the ideas. One, I've taught you guys that anytime a proportion is true, we can flip it over. So I will flip this proportion over to C plus D over C equals A plus B over A. All I did was reciprocate it. The next thing we can do with this proportion is we can write each side with a common denominator. The common denominator C could be seen as C plus D over C equals A. Oh, I wrote that wrong. Let me say that again. C over C plus D over C equals A over A plus B over A. We're so used to putting them together we forget that we can bring them apart. Now what I notice is that this is a 1 and this is also a 1. If I subtract 1 from each side, I have a new proportion. D over C equals B over A. Alright, so let's flip it one more time. Let's flip it back over. C over D equals A over B. Now you don't have to do this work. This was the proof of the side-splitter theorem. What I want us to see is, look, C over D equals A over B. The proportion was there for us the whole time because the side splits it into proportional parts. The side splits into proportional parts. So I'm going to erase the proof now. That was the idea that you got to look at and see. And what I'm going to do now is I'm going to say the side splitter theorem says C over D equals A over B, and we're going to put in some real numbers. Here's 5, 10, we'll call this X, and we'll call that 16. And now we need to solve for X. We don't have to get into 5 over 5 plus 10 equals X over X plus 16. We can simply go to X, which is C, over 16 equals 5 over 10. This only works for the sides cut by the parallel line. It does not work for the bases. Cross multiply, we've got 10x equals 80, and divide by 10, and our second example is done. X equals 8. Our last example on the board for now is, what about multiple parallel lines? This is similar to the side splitter theorem, but look, there's no triangle in this picture. Or is there? I have parallel lines here, but if I continue these transversals, eventually they will meet. And now I see a triangle. And if there's a triangle, then the side splitter theorem must apply. Which means the length of 4 is proportional to 5, the same way 6 is proportional to x. And we can cross multiply again. 4x is equal to 30. We divide by 4, and in this case, it comes out to 7 1/2. And there's another application of similar triangles, although we had to sort of finish the triangle on this problem. We have one more example using the angle bisector theorem, and we'll set that up now. Okay, here's our final example for this lesson. We have here a triangle with an angle bisector, and there's the two congruent angles here. So because of that angle bisector, we're going to try to figure out if there is some kind of relationship A, B, C, and D. What we're looking at is that there is a theorem out there that says if a line bisects an angle in a triangle, then it splits the opposite sides proportional to the adjacent sides. What I've done to at least show this so that we can see the idea is I created a parallel line to the angle bisector. I just created this. I added it to the picture. And then I extended this side with A up until it hit it. What I noticed is because of the parallel line, this angle right here and this angle right here are alternate interior angles, and they are congruent. I also know that this line right here is a transversal, and this line angle right here and that angle right there are corresponding. Now through the transitive property, I've got all 4 of these angles exactly the same. What I'm hoping some of you see is that with these 2 angles the same, this is a little isosceles triangle right here. And that makes this D. And now, if that's D, we have the problem from the previous board. We have the side splitter theorem. A over D equals B over C. So I can write A over D equals B over C. Now, one of the cool things about proportions is because cross multiplication, A times C equals B times D, I can flip these. Sorry, not D. I can flip this to A over B equals D over C. And now, all of a sudden, I see that the proportion was there the whole time. A over B equals D over C. And this right here is the angle bisector theorem. Let's see how it works in this problem. Angle bisector splits the adjacent side proportional to this opposite side. 6 over 5 equals 5 over x. Sorry, said that completely wrong. 6 over 5 equals x over 8. We get 5x is equal to 48. We divide by 5, and we get x is equal to 9 3/5. That's it for Chapter 7, Section 5. You can now begin working on that assignment.